Okay, so previously we looked at how we could add on that water in a hydration reaction with our carbonyl compounds. Now next we can look at how that reaction will be affected by the structure of our carbonyl, right? So whether we're following the basic path over here on the left, or if we're following the acidic path over here on the right, in both cases, we're attacking that electrophilic carbon with our either our water or our hydroxide as our nucleophile. Right, so we'd have hydroxide coming in here and attacking, or on the acidic pathway, we'd have our water coming in and attacking over here on the other side. Okay, so what would affect that attack? The key things that will affect that will be the capability of our nucleophile to come in there and attack that site. And then also how strongly electrophilic our carbon is. So the first key thing that affects any nucleophilic attack is crowding. Right? If we have steric crowding near that reactive site, it can block that nucleophile as it's trying to come in and attack that site, and therefore slow down the reaction. So if we compare our formaldehyde up here, formaldehyde is not very crowded at all, right? It has two hydrogens connected here at this carbonyl carbon, and there's lots of room for a nucleophile to come in and attack. If we compare our formaldehyde to a ketone, with a ketone we have these methyl groups here on either side of that electrophilic carbon that we're trying to attack. Right, so here's our attack site here, our electrophilic carbon, and these methyl groups on either side can slow down the attack. So whenever we're comparing aldehydes, such as our formaldehyde here, versus ketones, this would be our acetone here, the rate of hydration, and therefore the amount of hydrated product that will form, will be much higher for our aldehydes compared to our ketones. Now within our aldehyde or our ketone classes, we can also change the amount of crowding at that electrophilic carbon by changing, of course, what groups are attached. For example, if we look at the following ketone with T-butyl groups attached on either side of that electrophilic carbon, we've got our electrophile in the middle, and we've got huge groups that will block the attack. This will then have a very slow hydration rate. So similar to any nucleophilic reaction, an SN2 reaction, or many of our other nucleophilic reactions that we've looked at, the more crowding you have at that site, the slower that reaction is going to be, and therefore the less of your product you'll actually see produced. So something like this would have a very slow reaction. You'd see very little hydration. Our acetone here is less crowded because we only have our methyl groups here instead of our T-butyl groups. So that would have a somewhat faster reaction, and our formaldehyde would have the fastest reaction of all, comparing our different carbonyls here. Okay, so our first factor is that crowding, where the more crowded it is, the more difficult it is for our nucleophile to attack. The second factor is the strength of our electrophile. So if we have a better electrophile, then our nucleophile is going to have an easier time attacking, and so we'll see more hydration. Now, of course, we're always looking at our at a carbonyl, right? So you might think, how can you change that electrophile and make it more electrophilic without changing the fact that it's a carbonyl, the carbon double bonded to oxygen? Well, what we can do is add electron withdrawing groups. So if we take our electrophilic carbonyl carbon and we attach some fluorines nearby, fluorines, as we know, are highly electronegative, right? So each of these fluorines are going to be pulling away electron density, acting as electron withdrawing groups. And so overall, we're going to be increasing the electrophilic nature of our carbon here. So we make a stronger electrophile by pulling away that electron density. So we pull away all that electron density with our fluorines, and now we've made this much stronger electrophile. So now when we're bringing in our nucleophile in our basic hydration reaction, this attack is going to be a lot faster, and therefore we'll have a higher rate and a higher amount of our hydrated product produced. So again, if we look at the rate of hydration, we have carbonyls with electron withdrawing groups. Will have a greater rate than our carbonyls without electron withdrawing groups. So these two main factors, crowding and the strength of our electrophile, which is affected by electron withdrawing groups, will have a large effect in the rate of our reactions with our carbonyls, specifically hydration, but we'll also see that this will have a similar effect with other reactions as well, which we'll look at later.